Next problem. Assume that a computer system is in any one of the three states, busy, ideal, and under repair, respectively, denoted as 0, 1, 2. Observing its states at 2 p.m. each day, we get the transition probability matrix as P is equal to matrix zero point 0.6, zero point 0.2, zero point 2, zero point 0.1, 0.8, 0.1, 0.6, 0.4. Find out the third step probability matrix, and second one determine the limiting probabilities or probability distribution after infinite number of steps, or find the steady state distribution of the chain. Now in the previous problem the states are 0, 1, 2. Here in this problem given that the states are 0, 1, 2. 0, 1, 2. In the previous case 1, 2, 3. Sorry, the previous problem we can take the states the 1, 2, 3. Now given the transition probability matrix is P is equal to state 0, 1, 2, 0, 1, 2. The matrix elements are 0 0.6, 0 0.2, 0 0.2, 0 0.1, 0 0.8, 0 0.1, 0 0.6, 0 0.4. Now the first problem is, here in this case, find out the third step probability matrix. Now that is to find third step transition probability matrices P of 3. What is Chapman-Kolmogg theorem? Chapman-Kolmogg theorem is n-step transition probability matrix P of n as P raised to n. N is the order of the matrix. P raised to n is the power of the matrix. Now that is here we can find the third step transition probability matrix P of 3 as P cube. We can find the matrix P cube. Now P3 is equal to P cube is equal to P square into P. That is P square is P into P as we can multiply these two matrices, that is to get 0.50, 0.28, 0.32, 0.20, 0.66, 0.14, 0.60, 0.12, 0.28. Now summing the each row, that is to get 1. Now we can find that third step transition probability is P of 3, that is P cube. That is P square into P. Now P square into P as we can simplify this matrix. There is 0.460, 0.324, 0.216, 0.270, 0.568, 0.162, 0.50 to 0.216, 0.24. See, here summing each row, there is the first row sum is 1, second row sum 1, third row sum 1. This is the property. Now the second part is, see, the given matrix, all the entries of the given matrix are positive. That means P has a regular matrix. That is also given the Markovian chain is regular. That means that the Markovian chain has a steady state distribution. That is pi is equal to pi naught, pi 1, pi 2. Here in this problem we can use the state 0, 1. So we can use notation pi 0, pi 1, pi 2. Our aim is to find the values of pi naught, pi 1 and pi 2. So we can use the following equations, solving the following equations, pi p equal to pi and pi naught plus pi 1 plus pi 2 equal to 1. Now the first equation, pi p equal to pi, that is pi as pi naught, pi 1, pi 2, p as 0 0.6, 0 0.2, 0 0.2, 0 0.1, 0 0.8, 0 0.1, 0 0.6, 0 0.1 equal to pi naught, pi 1, pi 2. Now multiply this matrix. The first equation has 0.6 pi naught plus 0.1 pi 1 plus 0.6 pi 2 equal to pi naught. That implies 4 pi naught minus pi 1 minus 6 pi 2 equals to equation number 1. Now the second equation is 0.2 pi naught plus 0.8 pi 1 equal to pi 1, which is that implies pi naught minus pi 1 equals to equation number 2. The next one, 0.2 pi naught plus 0.1 pi 1 plus 0.4 pi 2 equal to pi 2, that implies 2 pi naught plus pi 1 minus 6 pi 2 equals to equation number 3. Now from 2 we get pi naught is equal to pi 1, that is equation number 4. Substitute 4 in 1 and 3, we get equations 3 pi naught minus 6 pi 2 equals 0, that implies pi naught equal to 2 pi 2 equation number 5. Since pi naught plus pi 1 plus pi 2 equal to 1, that is denote equation star. Substitute 4 and 5 in star, we get pi 2 plus 2, pi 2 plus pi 2 equal to 1. That implies 5 pi 2 equal, that implies pi 2 equal to 1 by 5. Now, pi naught is equal to pi 1, which is equal to 2 pi by 2, that is equal to 2 by 5. That is, the limiting probability distributions are pi naught equal to 2 by 5, pi 1 equal to 2 by 5, pi 2 is equal to 1 by 5. This is very important problem.